Greetings A-level students. Today we've got an orders of reaction question, and there's a reaction going on between hydrogen peroxide, Ki and H plus ions making I2 and water. So a researcher is performing several experiments to determine the rate constant for this reaction, and we're given a table which looks like this. So we've got the experiment number going from 1 to 4, might be called the run number, and we read across, we've got concentration data for all of our reactants. So there's H2O2, here's I minus, and here is H plus. And in the final column, we have the initial rate. And remember that the initial rate is given, just got to be pretty eagle-eyed here, as 10 to the minus 6. So this is actually 3 times 10 to the minus 6 when we're doing the calculation for the rate constant. If you don't do that, you're going to be orders of magnitude out. So what's the best approach to tackling a question like this? Well, we have to determine the orders of reaction with respect to each species. So we're looking for changing one of the variables while keeping all the other concentrations constant, okay? So for example, straight away I'm just looking at runs 1 and 2. And between run 1 and 2, I can see that my H2O2 concentration has remained the same, so multiplied by 1. I can see that my H plus concentration has remained the same, so we're not changing that, we're keeping that constant. However, what am I doing to the iodide concentration? To work out the scale factor, we can do 0.03 over 0.015, and that gives us a scale factor of 2. So we are doubling the I minus concentration, okay? Cool. So once we've done that, we now have to see how changing the I minus concentration affects the rate, if at all. So what we do is we go to the rates column and we see how going from 3 to 6 and see what that changes and try and calculate that change. So to work out the scale factor, it's going to be 6 over 3. The 10 to the minus 6 will cancel out here. So that gives us a scale factor of 2, so we're doubling the rate. Well, now we can determine the order because we're also doubling the I minus concentration. So if we're doubling the I minus concentration, going from 0.015 to 0.03, and we're also doubling the rate, then we can say that is a linear relationship between the concentration of iodide and the rate. So as one changes, the other changes by the same proportion. So we can say that this is first order with respect to I minus. Okay. Where do we go next? So now that we've looked at I minus, I'm just going to tick that off. Let's figure out the relationship between the concentration and the rate for another species. So let's go for that color. Okay, so let's compare runs 1 and 3. Okay, doing red. So what's happening here is my I minus concentration is staying constant. My H plus concentration is staying constant. However, what we're doing to my peroxide concentration, we are doubling it. And now I have to see what happens to the rate as a result, what the effect is on the rate. So we're going from 3 to 6. So we're doubling it, and we're also doubling the peroxide concentration. So if we're doubling this and we're doubling this, we can also say that that is first order with respect to H2O2. So I'm just going to tick that one off. So now what I'm ideally looking for is if I keep the peroxide concentration and the iodide concentrations constant whilst changing my H plus concentration and seeing how only the H plus concentration affects the rate. So the only runs where the H plus concentration is changed is between runs 1 and 4. So let's go with this green color. Okay, so now let's have a look at runs 1 and 4. So to go from 0.2 to 0.4, to work out the scale factor, you do 0.4 divided by 0.2, so that will give you a scale factor of 2. I'm doubling the H plus concentration. Okay, ideally we'd keep the iodide concentration the same, and we do. However, it might be, as in this scenario, we have to change the H2O2 concentration as well. But that's no dramas because I know what the order is with respect to H2O2. So I'm doubling the H2O2 concentration. Okay. I'm just going to put this, hopefully. I'll get rid of that for a second. Okay, so what's happening? Now I'm doubling the H2O2 concentration, so that means the rate has to also double, okay? So if I double the rate going from 3, I get to 6. Now I'm doubling the H plus concentration as well. I'm doubling that. However, the final rate is 6, and that's a result of doubling the H2O2 concentration because it's first order, right? So what we're saying here is, even though we're doubling the H plus concentration, that's having no effect on the rate, because if it was, then we would expect, if it was first order, for example, with respect to H plus, we'd have to double this again. So 6 times 2 would be 12, and we don't end up with 12. Okay, so what can we say is it's 0 order. So it's 0 order with respect to H plus. That has no effect on the rate at all. So this is only due to the H2O2, which we know is first order. Okay, so let's just write this out. So first order with respect to H2O2 and I minus 0 order with respect to H plus. Okay, where do we go from this? Now I can write my rate equation. So my rate equals K. So only include the species which influence the rate, and that is H2O2, and I don't include H plus, because if I raise the concentration of H plus to the power of 0, it becomes 1, which is the number. So this is H2O2, don't need to put the 1, it's implied, and I minus. Cool, and that's it for determining the rate equation. Okay, so we also have to determine the rate constant. So what I'm going to do is rearrange for K. So to rearrange for K, we're going to divide through by the concentration of H2O2 and I minus. On both sides. So that's going to cancel out, that's going to cancel out, done. Okay, so first rearrange without putting any numbers in, okay? Now that we've rearranged, we can plug in some numbers. So K equals the rate over H2O2 and the I minus. So now what we do is just pick any run number you want. So let's go for run number 1. And what we're going to do is use data in run number 1 and use the data and substitute it into our rate equation. So the initial rate is 3 times 10 to the minus 6. Don't forget that, times 10 to the minus 6. Got some lovely color mixing going on over there. So my H2O2 concentration is 0.015. And my I minus concentration is also 0.015. So if you process this, you will get an answer of 0.0133. So we've determined the rate constant, but we haven't given the units just yet. So let's have a look at what our units are. So determine the units. Remember, the units of K vary depending on the overall order, right? So the rate always has units of moles per decimeter cubed per second, and concentration has units of moles per decimeter cubed. And for I minus also has units of moles per decimeter cubed. Okay, so this moles per decimeter cubed at the top can cancel out. And then if we bring this term up, because we've got the reciprocal, this is going to be mole to the minus 1 dm plus 3 s to the minus 1, and those are my units. Okay, thank you for watching. Ta-ta.